Hydrogen is often called the fuel of the future, but behind all the hype, there's real science that makes it possible. In this video, we'll break down how green hydrogen is actually made, the technologies behind it, and why understanding the basics of electrolysis, fuel cells, and storage is key to unlocking its potential. By the end, you'll see why hydrogen is not just an idea, but a powerful piece of the clean energy puzzle. So let's start with the big question. What makes hydrogen so special? Hydrogen isn't a primary source of energy like sunlight or coal. Instead, it's what we call an energy carrier. Think of it like electricity. It doesn't occur naturally in large amounts. But once we produce it, hydrogen can store energy and deliver it exactly where it's needed. The difference is that electricity flows through wires, while hydrogen carries energy through molecules. That makes it flexible and powerful, because it can serve industries that electricity alone struggles to reach. Now, how do we actually produce hydrogen in a clean way? The process is called electrolysis. The word literally means splitting with electricity. Inside a device called an electrolyzer, renewable electricity from solar or wind is used to split water into its two elements, hydrogen and oxygen. The reaction looks like this. H2O becomes H2 plus O2. The oxygen can be safely released while the hydrogen is captured and stored as a clean fuel. To make this work, an electrolyzer uses two electrodes, an anode where oxygen is released and a cathode where hydrogen is formed. These are separated by a membrane that keeps the gases apart but allows charged particles to flow. It's a simple reaction, but when you scale it up, it can power industries, transportation, and even entire cities. There are three main types of electrolyzers being used or developed today. The first is the alkaline electrolyzer. This is the oldest technology, proven and reliable, using a liquid alkaline solution to conduct electricity. It's cost-effective, but not as good at handling fluctuating renewable power. Next, we have the proton exchange membrane, or PEM electrolyzer. This one uses a solid membrane, making it compact and fast to respond to variable energy inputs like solar or wind. The challenge is that it relies on precious metals like platinum, which makes it more expensive. Finally, there's the solid oxide electrolyzer, or SOEC. This one runs at very high temperatures, which boosts efficiency, especially if waste heat is available. It's still in development, but it's considered one of the most promising technologies for the future. Now, you might be wondering, how much does it take to actually make hydrogen? Producing just 1 kilogram of hydrogen requires about 9 liters of ultra-pure water and around 50 to 55 kilowatt-hours of electricity. To put that in perspective, 1 kilogram of hydrogen has roughly the same energy as a gallon of gasoline. But unlike gasoline, when you use hydrogen in a fuel cell, the only emission is pure water vapor. That brings us to the next step, how we use hydrogen. To turn hydrogen back into electricity, we use fuel cells. In fact, a fuel cell works like a reverse electrolyzer. Instead of using electricity to split water, it combines hydrogen with oxygen to generate electricity, heat, and water. The reaction is simple. Hydrogen plus oxygen equals water plus power. Fuel cells are already being used in hydrogen cars, buses, and even backup power systems for buildings. They're quiet, efficient, and the only byproduct is water. But producing hydrogen is only half the challenge. We also need to store and transport it. Unlike electricity, which flows instantly through power lines, hydrogen must be physically stored and moved. There are several ways to do this. Hydrogen can be stored as a compressed gas, held under high pressure in tanks. It can be cooled to extremely low temperatures to become liquid hydrogen, which is energy-dense but expensive to keep cold. Or it can be bound into chemical carriers like ammonia or methanol, which are easier to ship and store. Each method comes with trade-offs in cost, efficiency, and complexity. Of course, none of this is perfectly efficient. At every step, splitting water, compressing hydrogen, moving it, and then using it in a fuel cell, energy is lost. Today, The full cycle efficiency of green hydrogen is only around 25 to 35% compared to direct use of electricity. That's why hydrogen is best suited for the parts of our economy that can easily run on electricity, like heavy industry and long-distance transport, instead of being used everywhere. So why does this science matter? Because it explains both the promise and the challenges. It shows us why hydrogen isn't cheap yet, why it requires clean water and lots of electricity, and why it can't simply replace all fossil fuels overnight. But it also shows why researchers, companies, and governments are investing billions into making it work. Electrolyzers are getting cheaper, fuel cells are becoming more efficient, storage methods are improving, and as these technologies mature, green hydrogen is becoming one of the most exciting tools in the fight against climate change. The bottom line is this: green hydrogen is not magic. It's chemistry and engineering applied at massive scale. But if we get it right, it could become one of the most powerful fuels of our lifetime. If you found this breakdown helpful, you'll love our full green hydrogen project development and financing course at H2 Hub, Rene Energy. We go beyond the basics into project life cycles, feasibility studies, financing, and real-world case studies. Make sure to like this video, subscribe to the channel, and share it with anyone who wants to understand the science behind the hydrogen revolution.